everyone, and welcome to the last chapter of our Physics O-Level lessons. Congratulations on completing this O-Level lesson series with me. It has been very fun throughout this series, learning different topics of this amazing form of science, physics. So it has brought us to this last chapter, and yet another very fun chapter, radioactivity. So in this, we're going to see what radioactivity is, the background radiation, sources of artificial radiation, how we detect radiation, and the three types of radiation. After this, we're going to understand radioactive decay equations, deflecting radiation, what is the penetrating power of the three radiations. We're going to learn the ionization of these types of radiation. Then we're going to see what radioactive decay is and half-lives, how we measure these half-lives, what radioisotopes are, what are the uses of radioisotopes, and in the end we're going to learn about nuclear fission, nuclear fusion, and nuclear power stations. So this is going to be all about radioactivity. So let's start. First, we need to distinguish between two things: radioactive substances and the radiation they give out. So many naturally occurring substances are radioactive, but usually these are not very concentrated so that they do not cause a problem. But there are two ways in which radioactive substances can cause us problems. One, if a radioactive substance gets inside us, its radiation can harm us. So when a radioactive substance gets inside us, we will say that we have been contaminated. And two, if the radiation they produce hits our bodies, we say that we have received a dose of radiation. We have been irradiated. So contaminated and irradiated are two different things. Contamination occurs when a radioactive substance gets inside us, and irradiation occurs when the radiation hits our bodies. So it doesn't get inside us, but it hits our bodies from the outside. So we have been irradiated. So speaking of irradiation, it is a fact that we are exposed to low levels of radiation all the time. This radiation is known as background radiation. It's in the atmosphere all the time, and we are exposed to it. So we are getting irradiated, and it is obviously harmful. In addition, we may be exposed to radiation from artificial sources as well, such as the radiation we receive if we have a medical X-ray. But of course, we don't have medical X-rays daily in our life, so that is not very harmful. But people who do the X-rays are exposed to that radiation, so they wear protective suits to keep them from being irradiated. So this background radiation that we are exposed to all the time is divided into natural background radiation, which is about 87% of the background radiation, and radiation from artificial sources, which is about 13%. So let's look at these sources one by one. The air is radioactive. It contains a radioactive gas called radon, which seeps up to the Earth's surface from radioactive uranium rocks underground. So as you can see, radioactive materials come from the ground, from rocks. We're going to see more about rocks later, especially uranium, and how this radioactivity was discovered. So this radiation contributes to about half of our exposure to background radiation, the radiation that comes from uranium rocks underground, and later becomes the radon gas in our atmosphere. So this is one source. The ground contains radioactive substances, and we use materials from the ground to build our houses. So we are exposed to radiation from these as well. So right now you're sitting in your house, you are exposed to radiation even while sitting in your house, because your house is also made up of the materials from the ground, and the ground contains radioactive uranium rocks. So in simple words, everything is radioactive. The atmosphere, and about half of our background radiation is divided into natural background radiation, and 13% is the radiation from artificial sources. So The ground is one source, and the things we make from the materials from the ground. So they contain radioactive substances. This is one source. Then we have our food and drinks. So our food and drink is also slightly radioactive because living things grow by taking in materials from the air and the ground. So they are bound to be radioactive. So then, inside our bodies, when we eat our food then exposes us to radiation. Now this is contamination. We say that we have been contaminated because the radioactive substance is getting inside us. So we are not being irradiated, we are not receiving doses of radiation like background radiation, but we are being contaminated by our food and drink as well. But this is only slightly radioactive. We're going to see the percentages of all these sources, how much they make up the background radiation. So our food and drink is the second source. Finally, radiation reaches us from space in the form of cosmic rays. So some of this radiation comes from the sun, some from further out in space. But thankfully, most cosmic rays are stopped by the Earth's atmosphere. If you live up a mountain, then you will be exposed to more radiation from this source because you're closer to the atmosphere. So, because natural background radiation is around us all the time, we have to take account of it in experiments. So it may be necessary to measure the background level and then to subtract it from the experimental measurements, any measurement we take. So these were the sources of background radiation. Here we have the percentages, a pie chart for these. So about half of this background radiation is because of the radon and thoron in the atmosphere. This is 51%. So the atmosphere is the main source of radioactive substances. Then we have the ground and the buildings, which make up 14% of the background radiation. Then we have medical, which is 12%. Cosmic rays are only 10%, as you can see, because most of these are stopped by the Earth's atmosphere, so they're pretty much lessened down. Then we have food and drink, which is 12%. Okay, I should have told the food and drink first because cosmic rays is less than food and drink. Medical and food and drink are equal, they are 12%, and cosmic rays are 10%. Then we have some very minute kind of sources, which are artificial sources. Let me say that. Food and drink, cosmic rays, ground and buildings, and radon and thoron are natural background radiation. But some of this background radiation also contains the artificial sources like air travel, TV sets, etc. These make up only 0.40%. But we also have radiation at work, which is 0.20%. Fallout from weapons tests, 0.40%. Then we have nuclear discharges, which is 0.10%. We're going to see what these all are. But for now, this is the pie chart for background radiation. So now we're going to see the artificial sources. So most radiation from artificial sources comes from medical sources. This includes the use of X-rays and gamma rays for seeing inside the body, and the use of radiation for destroying cancer cells. Medical, as we see here, makes up 12% of the radiation we receive, the background radiation. So they do help us in ways, but they are also sources of radioactive materials. They are still harmful. The weapon testing and nuclear discharging, they make up only 0.10 and 0.40%, which is really low. Because today most nuclear weapons testing is done underground. But in the past, bombs were detonated on land or in the air. And this contributed much more to the radiation dose received by people around the world. Now they are done underground, so it has decreased the percentage, decreased the radiation dose. Lastly, small amounts of radioactive substances escape from the nuclear industry, which processes uranium for use as the fuel in nuclear power stations, and handles the highly radioactive spent fuel after it has been used. So, nuclear weapons testing make up 0.40%, and nuclear discharges makes up 0.10%, which is really low. These substances, this is like the small amounts of radioactive substances which escape from the nuclear industry. The nuclear industry is very helpful in some ways because we use uranium for the use of the fuel in nuclear power stations. So there is less pollution by these compared to the coal power stations. Coal power stations create a lot of pollution because it is smoke and ash which gets released into the atmosphere. And so it makes the atmosphere more polluted compared to nuclear power stations. But yes, nuclear power stations also have their own hazards. Small leakages can make up a big disaster. Anyways, these were the sources of artificial radiation. So artificial radiation and natural background radiation make up this entire pie chart. The radiation we are exposed to all the time. So this pie chart is entirely background radiation. And this background radiation includes natural sources of radiation and some artificial sources of radiation like medicals, fallout from weapons tests, air travel, TV sets, etc. at work, and nuclear discharges. Then naturally we get them from the atmosphere, cosmic rays, food and drink, ground and buildings. So they're almost impossible to be avoided. Okay, now that we've understood background radiation and what radioactivity is, we're going to see how radioactivity was discovered, how it was detected. So, radioactivity was discovered by a French physicist, Henri Becquerel, in 1892. So his method was to leave a phosphorescent rock on his windowsill in the light. So phosphorescent rocks are rocks that glow for a while after they have been left under a bright light. So after leaving it on his windowsill in the light, he put it in a dark drawer on a piece of photographic film to record the light it gave out. So he suspected that rocks containing uranium might be good for this, giving out light in the dark. But he discovered something even more dramatic. The photographic film was blackened even when the rock had not been exposed to light. And so he realized that some kind of invisible radiation was coming from the uranium. And what was more, the longer he left it, the darker the photographic film became. So, uranium gives radiation all the time without any obvious supply of energy. This is what he concluded. So Becquerel had discovered a way of revealing the presence of invisible radiation using photographic film. So this method is still used today, but it takes a while to expose and develop a photographic film. So for quicker measurement of radiation, we can use a Geiger counter. So the detector is a Geiger-Müller tube, which is held close to a suspected source of radiation. The radiation then enters the tube, which produces an electric pulse every time it detects any radiation. So the electronic counter adds up to these pulses, and it gives a click or beep for each pulse. So nowadays this is what is used rather than the photographic film method Becquerel had discovered. Okay, this is how we detect radiation. We use a Geiger-Müller tube or the photographic film method to do so. And Henri Becquerel, the French physicist, discovered radioactivity in 1892. Now let's look at the randomness of radioactive decay. If you listen to the clicks and beeps of a Geiger counter, you may notice that it is impossible to predict when the next sound will come. This is because radioactive decay is a random process. So if you study a sample of a radioactive material, you cannot predict when the next atom will decay. Atoms decay randomly over time. And similarly, it is impossible to point at an individual atom and say that it will be the next one to decay. If an atom on the left of the sample has just decayed, we cannot predict that an atom on the right of the sample will be the next to decay. So as a result, if you count the number of particles from a source in, for example, 1 minute, the number will fluctuate, sometimes above and sometimes below an average value. So this is basically the randomness of radioactive decay. It cannot be predicted. So it's a very, very random process. So now we're going to see the microscopic picture of radiations. What these radiations are made up of. So, radiation is emitted by the nucleus of an atom. That is right, the nucleus of an atom. We say that the nucleus is unstable. Only an unstable nucleus emits radiation, just in an attempt to become more stable. Stable nucleuses do not need to emit radiation because they're already stable. Unstable nucleuses emit radiation in an attempt to become more stable. And so this is known as radioactive decay. So fortunately, most of the atoms around us have stable nuclei. So that is why we are not exposed to radiation that much. It's a very low level of radiation that we are exposed to. But most of the atoms around us have stable nuclei. When the Earth formed about 4,500 million years ago, like that's a lot of time, isn't it? There were many more radioactive atoms around. However, as those millions of years have passed, most have decayed to become stable. In the distant past, the level of background radiation was much higher than it is today. So now we're going to look at the three types of radiation. The radioactive substances emit three types of radiation, and these are named after the first three letters of the Greek alphabet: alpha, beta, and gamma. So alpha is represented by this kind of symbol. The symbol is named alpha. Beta has this symbol. Gamma has a Y kind of symbol. So alpha and beta are particles, whereas gamma is a form of electromagnetic radiation. If you remember the chapter Rays and Waves, we have read the electromagnetic spectrum and stuff and all the radiation. We have read in that chapter that gamma is the fastest radiation, and so gamma is also a radiation that is emitted by radioactive substances. So let's look at these three types of radiations one by one, starting with the alpha particle. So an alpha particle is made up of 2 protons and 2 neutrons. You may think this is the same as the nucleus of a helium atom because, well, it is a helium atom. So because it contains protons, it is positively charged. So this alpha particle is positively charged. Then we have the beta particle. So this beta particle is an electron. And of course, electrons, as we have read in previous chapters as well, electrons are negatively charged particles in an atom. But this electron, the beta particle electron, is not an electron that orbits the nucleus. It comes from inside the nucleus. So this is the whole thing. The nucleus is unstable, that's why a beta particle is being emitted by this atom. Otherwise, most atoms which are stable, they do not have any beta particles in them. So these beta particles come from inside the nucleus and they are negatively charged. And its mass is much less than that of an alpha particle. Of course, an alpha particle is made up of 2 protons and 2 neutrons. A beta particle is just an electron, and electrons are quite lighter than protons and neutrons, so its mass would obviously be less than that of an alpha particle. So this was the beta particle. Now we're going to see the gamma rays. So now we're going to see the gamma rays. Okay, so a gamma ray is a form of electromagnetic radiation. We can think of it as a wave with a very short wavelength, like a very high frequency, the fastest gamma ray as I was talking about. Alternatively, we can picture it as a photon. A photon is a particle of electromagnetic energy. So take it as a radiation or as a photon, it is a gamma ray, and it is the fastest of all radiations. Faster than the beta particle and the alpha particle, and lighter as well, that's why it is fast. So these were the gamma rays, the beta particles, the alpha particles. I hope you have understood all of them. All of them are different from each other. We're going to see more about them later, like their penetrating power and their ionization. So an atom of a radioactive substance emits either an alpha particle or a beta particle. In addition, it may emit some energy in the form of gamma ray. So the gamma ray is usually emitted at the same time as the alpha or beta, but it may be emitted sometime later as well. So alpha particles are the heaviest particles, so they travel more slowly than beta particles and gamma rays. Gamma rays travel at the speed of light, so gamma rays travel faster than both alpha and beta particles. So it's kind of like an order: alpha, beta, and gamma. Alpha is the slowest, beta is faster than alpha, and gamma rays are the fastest of all. So here we have a table which contains the information about the 3 types of radiations. The alpha particle has a charge of +2, the beta particle has a charge of -1, and the gamma rays have no charge and no mass because they are radiation. So this was alpha, beta, and gamma. I hope you have understood them. And now we're going to move ahead on to looking at some radioactive decay equations. So yes, even though it's all about information and radioactivity, we do have some decay equations, radioactivity. So when an atom of a radioactive substance decays, it becomes an atom of another element. So this is because in alpha and beta decay, the number of protons in the nucleus changes. So yeah, when an alpha particle is released, in other words, 2 protons and 2 neutrons are subtracted from the nucleus, and so obviously the protons in the nucleus change. So an atom's identity is known by the number of protons in its atom. So if the number of protons in an atom is 2, then it's going to be a helium atom, and if it is 3, then it is going to be a lithium atom. So when in alpha and beta decay, the number of protons in the nucleus change, then the atom becomes an atom of another element. But we say that it becomes stable then. After emitting radiation, it becomes a stable nucleus of another element. So here is an example of an equation for alpha decay. We're going to see the beta decay equation as well, but here we have the alpha one. Here we have the americium atom. So atoms are written like this. This 94 written over here is the proton number of americium, and the 241 written above is the nucleon number of americium. The nucleon number is in simple words, is neutron number plus proton number. That's the nucleon number, the collective number of neutrons and protons, whereas the proton number is just the proton number. So as you can see, an alpha decay has occurred with this americium atom, because americium is a radioactive atom. So americium releases an alpha particle. It changes into a uranium atom. So an alpha particle is 4 nucleons and 2 protons. So all we have to do is -4 from the nucleon number and 2 from the proton number, and we will get the atom of uranium. So whenever an atom is going through alpha decay, 2 protons are minus from the proton number and 4 is minus from the nucleon number. And then whatever numbers come, they would decide what atom has been made. So every atom has its own unique proton number. So if the proton number is 92, it is a uranium atom. If the proton number is 3, it is a lithium atom. 2 helium atom, of course, 1 hydrogen atom, and so on. So whatever the proton number would be, that will be the atom. So this is the equation. This is how we write the equation. Americium into uranium plus helium, the alpha particle, plus energy. And you know, energy is the gamma rays emitted. So this is alpha decay. Now remember, gamma radiation is released both in alpha decay and beta decay. But beta particles are never emitted in alpha decay, neither are alpha particles emitted in beta decay. These two are totally different. So alpha decay is a different thing and beta decay is a different thing. They two are never combined, whereas gamma radiation are always with both of them. So gamma radiation is energy emitted in both alpha decay and beta decay. But alpha decay is different and beta decay is different. Both beta particles and alpha particles cannot be emitted at the same time. Okay, so I hope that's clear. So this was the alpha decay. Now we're going to see the beta decay. Again, beta particles and alpha particles cannot be emitted together at the same time. It will either be the alpha particle or the beta particle. Whereas gamma radiation is emitted with both the beta particles and the alpha particles. So here we have the equation for beta decay. We have a carbon-14 nucleus, which decays to become a nitrogen-14 nucleus. So this is the decay that is used in radiocarbon dating. We're going to see what that is. It's very much related to carbon-14. So carbon has 6 protons and 14 nucleons. But remember, this is not the actual carbon atom. This is the carbon 14. And this is the carbon 14 nucleus we're seeing here. So when an electron has been released from the carbon 14 nucleus, it becomes a nitrogen atom, a nitrogen 14 nucleus. So the 6 protons become 7 protons. How is that possible, right? But if we could see inside the nucleus, we would see that a single neutron has decayed to become a proton. So this is what beta decay is. Neutron decays to become a proton. A proton plus an electron is released. So when an electron is released, neutron becomes a proton. The neutron becomes a proton. So this is what happens in beta decay. As you can see, the nucleon number doesn't change. It remains 14. Only the proton number changes. So this suggests that neutrons in the carbon atom are more than the protons. Of course, we can see this. The protons are 6 and the nucleon number is 14. So we minus 6 from 14 and what do we get? We get 8 neutrons. So 8 neutrons and 6 protons. This is what carbon atom is made of. Even though the actual carbon atom has a nucleon number of 12. So it's always equal. The protons and neutrons are always equal. But this is a carbon 14 nucleus. So this is an isotope of carbon. And it contains 8 neutrons and 6 protons. So when an electron is released, a neutron decays to become a proton. So the nucleon number doesn't change because only a neutron has become a proton. The number of neutrons and protons collective is the same. It is 14. But the proton number changes because one neutron has minus and one proton has increased. So one neutron into a proton causes the proton number to go to 7 from 6. So this might be a little confusing. But trust me, it's very simple. Try to understand. The carbon 14 is an isotope of the carbon atom. The carbon atom has a nucleon number of 12 and a proton number of 6. So that makes sense because every atom, every stable atom has equal numbers of neutrons and protons in its nucleus. Like a carbon atom would have 12 nucleons and 6 protons. So that will make sense. 6 plus 6 is 12. But in isotopes, the number of neutrons and protons are not the same. So here we have a carbon isotope. We call this isotope the carbon 14 because the nucleon number in this carbon atom is 14. Otherwise, it is always 12. So the carbon 14 has 14 nucleons, but the proton number is still 6. So this suggests that there are 8 neutrons in the carbon 14 nucleus. So there are more neutrons than the protons. The protons are 6 and the neutrons are 8. That is how the nucleon number becomes 14. So when beta emission occurs, an electron is released from the nucleus. So we don't count this electron in the nucleus because it is very light. But what happens is that when an electron is released, a neutron in the carbon 14 nucleus changes to a proton. But still, you can see that the nucleon number still remains 14 because it is the sum of the neutron number and the proton number. So the nucleon number remains 14, but the proton number changes to 7. So what happened is that the neutrons now in the nucleon number, the neutrons are now 7 and the protons are also 7. And so this results in a nitrogen atom. Because nitrogen's nucleon number is 14 and proton number is 7. 7 plus 7 is 14, so this is a stable nucleus of nitrogen. So this is how this happens. A neutron decays to become a proton and both the neutron number and the proton number become equal. 7, 7. Before, the neutron number was 8 and proton number was 6. One neutron got into the proton number. So the neutron number was 8, we minus 1 from 8 and it becomes 7. And the proton number was 6, we add 1 to 6 and it becomes 7. So 7, 7 and we get the nitrogen atom. So this is what beta decay is. It's much more confusing than the alpha decay, but if we understand it, it becomes really simple. So in the end of both the alpha decay and the beta decay, the atoms become stable atoms. The nucleuses become stable, but of course they do take the form of another atom because the proton number changes, but still at least they become stable after emitting beta or alpha radiation. Also, the equation contains energy, and this energy is gamma rays. So, for each of these two beta decay equations, this is one equation and this is one equation. You should be able to see that the nucleon numbers and proton numbers are balanced. So we say that in radioactive decay, nucleon number and proton number are conserved. When they become balanced after emitting the radiation, after the decay, proton number and neutron number are in balance. And so we say that the nucleon number and the proton number are conserved. So this was the radioactive decay equations. And they are very standard equations. Once you remember them, once you understand them, they'll become a piece of cake for you to remember. So now we're going to move ahead onto deflecting radiation. So deflecting radiation. To see the difference between these three radiations, one method is to see how they behave in electric and magnetic fields. So because they have opposite charges, an alpha particle is positive, a beta particle is negative, and gamma rays are neutral, all of these particles and rays are deflected in opposite directions when they pass through an electric field. So we are going to see the difference between the three radiations by this. So alpha particles, when they are passed through an electric field, are attracted towards the negatively charged plate. Okay, let me just show you a picture to make it easier for you to understand. Here we have the lead block. So we have put a lead block because these substances cannot get out from this lead block. They cannot penetrate the lead block. We're going to see more about the penetrating power of them as well. None of the substances, none of the radioactive rays can pass through this lead block. So that's why they are covered in this lead block. So the radioactive substances is passed through this block, and here we have two electrically charged plates. This is the positive plate and this is the negative plate. And here we have a photographic plate. On this plate we see where the radiations are going. So alpha particles are attracted towards the negatively charged plate because alpha particles are positive, so positive, negative, they attract. So it will go downwards like this towards the negatively charged plate, while beta particles are attracted towards the positively charged plate because they are negatively charged particles, so they will go upwards. And gamma rays are not deflected because they are uncharged. So alpha and beta particles are charged, so when they move, they constitute an electric current. Because of their opposite signs, the forces on them in a magnetic field are in opposite directions. So the directions in which the particles are deflected can be predicted using the Fleming's left-hand rule we read in the previous chapter. Okay, gamma rays are not deflected because they are uncharged. Alpha particles are being deflected downwards and the beta particles upwards. But you can see something here. As you can see, the beta rays are being attracted towards the positively charged plate more than the alpha to the negatively charged. So these beta rays are going upwards more than the alpha rays are going downwards. So the alpha rays do not deflect as much as the beta particles. The reason of this is because alpha particles are heavy. So alpha particles are the heaviest particles of all the three, and beta particles are lighter than the alpha particle, so they get deflected more than the alpha particle. Alpha particles are slow and heavy, so they do not get deflected as much as the beta particles. So here we see the rays being deflected. You may get questions related to these in your exams, so you have to remember which ray goes up and which ray goes down, and which ray goes up more or down more. So you can see that. For example, if the minus If the negatively charged plate goes upwards and the positively charged plate goes downwards, the gamma rays would still be in the straight line. The gamma rays are always in the straight line, remember, because they are not being deflected. But the beta particles would be here and the alpha particles would go upwards. But still, the beta particles would deflect more than the alpha particles. So that is how we can see which particles are which particles. So this is how the alpha particles, beta particles and gamma rays get deflected when they are passed through electrically charged plates. In the same way, if they are passed through magnets, two different poles of magnets, remember, the magnetic poles are up and down and the rays are passed in between them. So the rays do not move left or right. Like they do not move on the south pole's direction or the northward direction, they move up and down just like this, okay? So this electrically charged plates, we have to replace them with a north pole and a south pole. And so what will happen is that the alpha particle will move towards the south pole and the beta particle will move towards the north pole. The gamma rays would be undeflected. So alpha and beta particles are charged, so when they move, they constitute an electric current. So because of their opposite signs and this electric current, the forces on them in a magnetic field are in opposite directions. And so the directions in which the particles are deflected can be predicted using Fleming's left-hand rule. So this is how alpha, beta and gamma rays are deflected with magnets and with electric charges. So radioactive substances release energy when they decay. But before they decay, this energy is stored in the nucleus of the atom. So when it is released, it is in two forms. An alpha or beta particle is fast moving, so the nucleus that has emitted it recoils. Both particles have kinetic energy. Like what we are trying to say here is that when alpha or beta particles are released from a nucleus, two different forms of energy are also released. So before they decay, the nucleus of the atom stores energy, and this energy is released when the decay occurs. So for example, an alpha particle is emitted by an americium atom, like we read before in that equation. The nucleus emits this alpha particle and then it recoils and the alpha particle just moves outwards. So both of them, the nucleus as well as the alpha particle, has kinetic energy. The nucleus recoils, that emits the particle recoils, and alpha particles are fast moving, so they also have kinetic energy as well as the nucleus. And this is the same as for the beta particle. So the nucleus has kinetic energy. The second form of energy released is electromagnetic radiation. This is emitted by the gamma rays. Like in the equation, we saw that whenever an alpha or beta particle is emitted, a gamma ray also get emitted. And these transfer energy as electromagnetic radiation. So a gamma ray transfers energy as electromagnetic radiation. So these were the two forms in which energy is released when radioactive substances decay: kinetic energy and electromagnetic radiation. So now that we've seen the two different types of energy released from radioactive substances when they decay, and how radiation is deflected by electric charges and magnets, and the radioactive decay equations we've learned here, we are going to move ahead on to understanding the penetrating power of these radiations. When physicists were trying to understand the nature of radioactivity, they noticed that radiation can pass through solid materials. And different types of radiation can penetrate different thicknesses of materials. So, we're going to see the penetrating power of each of the radiation we just learned about: the alpha particles, beta particles, and gamma radiation. Starting with alpha particles. Alpha particles are the most easily absorbed. They can travel about 5 cm in air before they are absorbed. and they can be absorbed by a thin sheet of paper. So alpha particles are most easily absorbed because they travel slow. As you can see, they can travel about 5 cm in air before they are absorbed by it. And alpha particles cannot pass a thin sheet of paper. They get absorbed into it. But beta particles can travel fairly easily through air or paper. But they do get absorbed by a few millimeters of metal. The main reason of this is because beta particles move faster than alpha particles. Alpha particles are heavy, so they move slower. And so alpha particles interact with the air molecules and they get absorbed into it. We're going to see more about how the alpha particles and all these radiation interact with air molecules. And that's going to be related to the ionization of these radiation. But for now, we should know that beta particles can travel through air or paper, but they do get absorbed by a few millimeters of metal. And alpha particles can travel about 5 cm in air before they are absorbed, and they can be absorbed by a thin sheet of paper. Then we have gamma radiation. Gamma radiation is the most penetrating. It takes several centimeters of a dense metal like lead or several meters of concrete to absorb most of the gamma radiation. In simple words, gamma radiation does get absorbed by lead as well as concrete, but it passes paper and aluminium. Aluminium is a light metal. It's not a dense metal like lead. But yes, it does take several centimeters of the dense metal lead or several meters of concrete to absorb most of the gamma radiation. Gamma radiation is the most penetrating. Again, it is fastest of all the radiations. So here you can see an alpha particle. It gets absorbed by this thin sheet of paper. The beta particle penetrates through the paper but gets absorbed by the aluminium, the light metal. Gamma rays penetrate through paper as well as aluminium, but they get absorbed by lead. Then we have neutrons. They can travel through lead as well, but they get absorbed by concrete. So in the end, nothing can pass through concrete, any kind of radiation. So these were the penetrating powers of these radiation. Alpha has the least penetrating power and gamma has the most. So this was it was very simple. Now we're going to see the ionization of these radiations. We understood that when radiation passes through air, it can get absorbed, like alpha particles get absorbed when they travel about 5 centimeters in air. What happens is that when radiation passes through air, it may interact with air molecules, knocking electrons from them so that the air molecules become charged. So we say that the air molecules have become ionized. Okay, so here we have the relative ionizing effects. Alpha particles are the most ionizing and gamma radiation is the least ionizing. So why is this? Usually gamma radiation is the fastest radiation and stuff and all that. But why is gamma radiation is the least ionizing and alpha particles the most? Because alpha particles move slowly and gamma radiation is fast. So the reason why alpha particles are the most ionizing is because they have the largest charge and they are the slowest moving of all three particles. And gamma radiation is uncharged and it is the fastest moving, so that is why it's least ionizing. So because the radiation from radioactive substances causes ionization of the materials that absorb it, it is often known as ionizing radiation. Let's look into more detail of how all of these particles ionize air. An alpha particle is the slowest moving of all three particles and has the largest charge. So as the alpha particle collides with an air molecule, it may knock an electron from the air molecule so that it becomes charged. The alpha particle loses a little of its energy, so it must ionize thousands of molecules before it loses all of its energy and comes to a halt. Nonetheless, alpha radiation is the most strongly ionizing radiation. So, whenever an alpha particle or the beta particle knocks electrons from air molecules, it loses a little of its energy as well. It keeps on ionizing molecules before it loses all of its energy and comes to a halt. But because alpha particle is the slowest moving of all three particles and has the largest charge, the more time it takes to move through air, the more interaction it will have with the air particles. If it is a fast moving particle, then it is most likely to travel straight past an air molecule without interacting with it. So alpha particle is slow, so it does interact with different air particles. And also it has the largest charge, that is also one reason. So that is why alpha radiation is the most strongly ionizing radiation. Then we have the beta particle. The beta particle can similarly ionize air molecules. However, it is less ionizing for two reasons. Its charge is less than that of an alpha particle. We know that it's an electron. An alpha particle is positively charged because it has 2 protons and 2 neutrons. I mean, neutrons are neutral particles, but there are 2 protons, so it has more charge than a beta particle, which has only 1 electron. One reason is that its charge is less than that of an alpha particle, and the second reason is that it's moving faster, so that it is more likely to travel straight past an air molecule without interacting with it. So this is why beta radiation can travel further through air without being absorbed. See? We can see the penetrating power coming in over here as well. Because alpha particle is strongly ionizing, firstly because it is slow and has the largest charge, that is why alpha particles are the most easily absorbed in air as well. Whereas beta particles are less ionizing, and so they can travel further through air without being absorbed. Then we have the gamma radiation. Gamma radiation is uncharged and it moves fastest of all, so it is least ionizing. No charge means no interaction, and because it is fast, it travels straight past an air molecule without interacting with it. And I mean, if it is not charged, then how would it interact? Well, it's not possible. So lead is a good absorber because it is dense and its nuclei are relatively large, so they present an easy target for the gamma rays. That's why gamma rays get absorbed into lead. So you should be able to see the pattern linking ionizing power and absorption. Alpha radiation is the most strongly ionizing, so it is the most easily absorbed and the least penetrating. Gamma radiation is the least strongly ionizing, so it is the least easily absorbed and most penetrating. Okay, so this was ionization. Do you know that X-rays also cause ionization in the materials they pass through? And so they are also classed as ionizing radiation. Well, X-rays are very similar to gamma rays, but X-rays usually have less energy. That means they have a longer wavelength than gamma rays, and they are produced by X-ray machines. They're also produced by stars and many other things, rather than by radioactive substances. So X-rays do not get produced by radioactive substances. They are produced by machines and stars and so on. Okay, so remember, when something has been exposed to radiation, we say that it has been irradiated. Although it absorbs the radiation, it does not itself become radioactive. Things will only become radioactive if they absorb a radioactive substance. So, you do not become radioactive if you absorb cosmic rays, which you do all the time, don't you? But the thing is that the cosmic rays get absorbed by the layer of dead skin cells we have on our body and also our clothes. So, being irradiated means that we are exposed to radiation. But when we say that we have been contaminated, that means that we have absorbed a radioactive substance, either eaten a radioactive substance or breathed in. So we do breathe the air, and the air contains radioactive substances like the radon and thoron gases. They are radioactive. So in that case, we are being contaminated all the time. We breathe in and we breathe out, and so this air and these radioactive substances go inside our lungs and in our bloodstream. Also, we have foods. We eat foods which also contain radioactive substances. So we do become radioactive when we consume a radioactive substance. But it is not that much. In food, there's very less radioactive substance. It isn't that harmful because the radioactive substances are very less. The most amount of radioactive substances we get is from the air that we breathe in. That makes up about 50% of the background radiation we are exposed to and we also absorbed. So, knowing about the radiation produced by radioactive materials tells us how to handle them as safely as possible so that we do not get contaminated or irradiated. This is where safe handling comes in. When we are handling different radioactive sources, what are the things that we should do to keep ourselves safe from these radioactive substances? So radioactive sources should be stored in a container that will absorb as much as possible of the radiation coming from them. So lead is a good material for this because all the 3 types of the radiation get absorbed by lead. So it is a strong absorber of all 3 types of the radiation. That is why usually the containers that are made to store radioactive sources are made from lead. So each source is kept in its own lead-lined compartment, and the whole box should be stored in a metal cabinet with a hazard warning sign so that nobody would open it. When sources are not in their protective container, that is when they are being experimented on, they should be handled very carefully. To avoid contamination, tongs can be used so that the user does not come into direct contact with the source. During any experiment, the user should stand at a safe distance from the source. So this was it for safe handling. I hope you've understood the ionization and the penetrating power of radioactive substances. These are quite related to each other, ionization and penetrating power. So now that we've understood them, and also how we can handle these radioactive substances safely, we are going to move ahead onto understanding radioactive decay. So Henry Becquerel discovered the radioactivity of uranium. What surprised him was that the uranium appears to be able to emit radiation endlessly without ever running out of energy. And so this would go against the conservation of energy, that the energy is conserved, and when it is released, it starts to get less and less until it ends completely. So what Becquerel did not realize was that the uranium he used was undergoing very gradual radioactive decay. So we know that radioactive decay causes energy to be released. But some substances like uranium undergo very slow and gradual radioactive decay, and so they appear to be able to emit radiation endlessly. But they do get run out of energy too. So here you can see the graph of radioactive decay of strontium. This is a different, but it is the same for any other radioactive substance. That the amount of a radioactive substance decreases rapidly at first and then more and more slowly. In fact, because the graph tails off more and more slowly, we cannot say when the last atoms will decay. So, different substances decay at different rates, some much faster and some less. But there is a pattern in which radioactive substances decay. Here we have 100 atoms of strontium, for example, and after 25 years they get to 50. Then after 50 years they get to 25. After 75 years they get 12.5, and so on. So you can see that after each 25 years, half of the atoms of strontium decrease. Like after 25 years there were 100 and they got to 50. Then 50 years they went to 25. So when we half 50 we get 25. Then we get 12.5. They are halved after every 25 years. So this is a pattern in which radioactive substances decay. Okay. Because we cannot say when the substance will have entirely decayed, we can identify the half-life of the substance. So this graph keeps on going and it tails off more and more slowly. So we can never predict when the substance will be entirely decayed. And so to find out this, that when the substance will be entirely ended, you can identify the half-life of the substance. So the half-life of a radioactive substance is the average time taken for half the nuclei in a sample to decay. So this is what a half-life is. When half of the nuclei in a sample decays, that's the half-life of a radioactive substance. It is the average time, remember, it's not a specific time, it's an average time because the time can vary from element to element. So we might know the half-lives of uranium, the half-life of americium, or any other radioactive substance. So uranium decays slowly because it has a very long half-life. The radioactive samples used in schools usually have half-lives of a few years, so that they have to be replaced once in a while. Some radioactive substances have half-lives that are less than a microsecond. So no sooner are they formed than they decay into something else. Okay, so I hope you've understood what radioactive decay is, that any radioactive materials decays, and the average time taken for half of the nuclei in a sample to decay is the half-life of a radioactive substance. We are going to see how we can explain half-life, and let's dive into the details of half-life. Okay, so you might be thinking that if the half-life of a radioactive substance is the average time taken for half of the nuclei in a sample to decay, then 2 half-lives would be required for the radioactive substance to be entirely decayed. But that's not true, okay? So after 1 half-life, half of the atoms in a radioactive sample have decayed. However, this would not mean that all of the atoms will have decayed after 2 half-lives. So let's see this in more detail. Say for example, we picture a sample of 100 undecayed atoms of a radioactive substance. They decay randomly. Each one has a 50-50 chance of decaying in the course of 1 half-life. So, what happens is that at the start, there are 100 undecayed atoms. This is the first stage. Then, after 1 half-life, a random selection of 50 atoms has decayed. So, that half of the atoms have decayed. But now, during the next half-life, a random selection of half of the remaining 50 atoms decays, leaving 25 undecayed atoms. So, in the next half-life, a random selection of half of the remaining 50 atoms. So what happens is that in each half-life, half of the remaining atoms decay. So at the start there were 100, after 1 half-life they remain 50. Then, this is the second half-life in which half of the remaining 50 atoms decay, that leaves 25. During the third half-life, half of the remaining atoms decay, leaving 12 or 13. Of course, we cannot have half an atom. That's not possible. So yes, it leaves 12 or 13. So the number of undecayed atoms goes to 100, 50, 25, and then to 12, and so on. This is how the half-lives go. So you can see that at first, when we take this information and put it into a graph and make a graph out of it, you will see that the graph is steeper at the beginning, but then it becomes slack, and the graph tails off more and more slowly because half of the atoms keep on decaying. So it's never the entire pack of atoms. It is always half the atoms that decay in 1 half-life. So the number of undecayed atoms goes from 100 to 50 to 25 to 12 and so on. It is because radioactive atoms decay in a random fashion that we get this pattern of decay. Notice that just because one atom has not decayed in the first half-life does not mean that it is more likely to decay in the next half-life. It has no way of remembering its past. So, usually, we cannot measure the numbers of atoms in a sample. So instead, we measure the count rate using a Geiger counter or some other detector. We might also determine the activity of a sample. This is the number of atoms that decay each second and is measured in becquerels. So we cannot measure the number of atoms in a sample. Of course, we cannot count the atoms. So instead we measure the count rate. We use a Geiger counter and we record the beeps of the Geiger counter. Each beep represents an atom decaying. So whenever an atom of the radioactive substance decays, the Geiger counter beeps. So that is how we measure the count rate of a radioactive sample rather than counting the actual atoms of the sample. So an activity of 1 becquerel is 1 decay per second. So the count rate and activity both decrease following the same pattern as the number of undecayed atoms. Okay, so this is how we measure the numbers of atoms in a sample. Okay, so now we're going to do this question and see how we can solve it. It is related to the half-lives we read just now and understood. So a sample of radioactive element X has an activity of 240 becquerels. So we know that an activity of 1 becquerel is 1 decay per second. This radioactive element has an activity of 240 becquerels. So this suggests that 240 atoms decay per second of this element. So if the half-life of X is 3 years, what will its activity be after 12 years? This is what we're going to find out in this question. So, step 1, we're going to calculate the number of half-lives in 12 years. So if the half-life of X is 3 years, we're going to divide 12 years with 3 years, and what we get is 4 half-lives. So to find out what the activity of this radioactive element would be after 12 years, we divide 12 years by 3 years. So 3 years is the half-life of the element, and we divide 12 years with 3 years, and what we get is 4 half-lives. So if we want to know what the activity would be after 12 years, this means that 4 half-lives will be passed after 12 years. Hence, we want to know the activity of the sample after 4 half-lives. In the step 2, we calculate the activity after 1, 2, 3 and 4 half-lives. So what we do is that we divide by 2 each time. So if the initial activity is 240 becquerels, the activity after 1 half-life would be 120 becquerels. So what we did is divided 240 by 2 and we get 120. Then the activity of after 2 half-lives would be 60, because then we divide 120 by 2. We're going to divide 60 by 2, we get 30. Divide 30 by 2, we get 15 becquerels. So the activity of the sample has fallen to 15 becquerels after 12 years. So this is how we find the activity of a sample. So what we did is that we first found out how many half-lives, because we know the half-life of the element X is 3 years. So then we found out how many half-lives would be passed after 12 years of its activity. And by dividing 12 years by 3 years, 3 years is the half-life, and we want to know the activity after 12 years, so we divide 12 by 3 and we get 4 half-lives. So that means that after 12 years, the element X would have crossed 4 half-lives. So if right now the radioactive element has an activity of 240 becquerels, then we divide 240 becquerels 4 times. And so after dividing it 4 times, in the end, we get 15 becquerels at the end. First of all, after 1 half-life, the activity would decrease down to 120 becquerels, and then after 2 half-lives, it will decrease down to 60 becquerels, then to 30 becquerels after 3 half-lives, and after 4 half-lives, we'll get 15 becquerels. So the activity of the element X after 12 years, that is 4 half-lives, it would be 15 becquerels. Okay, so this is how we measure the activity of any element after a known time, if we know the half-life of the element. So I hope you've understood how we do this. Now we're going to see how we can measure a half-life in the lab. So the half-life of a particular substance like protactinium 234 is measured in the lab. So this is the apparatus we use. This is the Geiger-Müller tube. This is the Geiger-Müller tube. And here we have the protactinium in this bottle. So after the bottle has been shaken, the upper layer of liquid contains protactinium, which emits beta radiation as it decays. So because the half-life of protactinium is 70 seconds, the count rate decreases quickly. So the number of counts in successive intervals of 10 seconds is recorded. Then we plot this graph which shows the number of counts in each interval against time. So the half-life then can be deduced from the decay graph. So this is the graph. So these are the counts in 10 seconds and this is the time, seconds. So at first, this is how we plot a graph of number of counts in each interval against time. How we can measure a half-life in the lab. This is how we do it. We can measure the counts of decayed atoms in successive intervals of 10 seconds. Okay, so now that we've understood how we can measure half-lives, both by the equation, I mean this is not really an equation, but this is a method of measuring half-lives in a known time. We're going to move ahead now on to understanding what radioisotopes are. So what isotopes are? Let me just explain that. Isotopes are the atoms of the same element but a different nucleon number. So you see, this is how atoms are written as. This is the carbon atom as you can see, and whenever we're talking about an actual atom, not an isotope of an atom, the proton number and the neutron number in that atom are equal to each other. So this number right here, the top number, is the nucleon number. This is the number of neutrons plus protons. The sum of the proton number and the neutron number is this. Whereas the lower number here is the proton number only. So we can find out the neutron number by subtracting the proton number by the nucleon number, and we'll get the neutron number, and that would also be 6. So an isotope is the atom of the same element but a different neutron number. Okay, so if the proton number would be changed of an atom, then the atom would become of a different element. So the proton number decides the element of the atom. So if it is 7, say for example the proton number becomes 7, then this atom would no longer would be a carbon atom. It would become a nitrogen atom. So for an element to have different forms, or in other words isotopes, neutron number changes. So here we have the carbon, and this carbon has 2 stable isotopes. We're talking about stable isotopes here. They're not radioactive. If they were unstable, they would be radioactive. So this is the carbon atom, and carbon 13 and carbon 14 are the isotopes of carbon. Okay, so carbon 13 is a stable isotope of carbon, but carbon 14 is an unstable isotope, and this is radioactive. So in the previous equation, this equation that we were learning about beta decay, here we have the carbon 14 atom, which turned into the nitrogen atom when it got stable. After beta decay, it became a nitrogen atom because the number of protons changed. So whenever the number of protons change in an atom, the atom's element changes simply. So the proton number is what tells the element of an atom. Proton number 6 presents the carbon atom, proton number 7 presents the nitrogen atom. So this is how it is. Isotopes are the atoms of the same element but a different neutron number. I also explained this before, but I'm doing it again so that it's easier to understand. So here we have carbon 13. The actual atom is carbon 12. The carbon 12 is an actual atom, but in carbon 13 the proton number is still the 6, but the nucleon number changes to 13. So this suggests that the neutron number has increased. So when we minus 6 by 13, we'll get 7. So 7 neutrons are in the carbon 13 atom. So you see the neutron number changed. Then in this carbon 14 atom we have 2 extra neutrons in it, which makes this the isotope of carbon. So different elements have different isotopes. Some may be stable but others are unstable. So that would mean that they are radioactive. Okay, so unstable isotopes are known as radioisotopes. These are what radioisotopes are basically. Radioisotopes are unstable isotopes, as the name suggests. So यार एक मिनट ना, अब आपने रोटी बनानी कि नहीं बनानी? रोटी बनानी होगी खाने के बदले. So the safe handling of radioisotopes requires an understanding of how radiation affects cell. So there are 3 ways in which radiation can damage living cells. Let's see them one by one. Let's look at them one by one. Number 1, an intense dose of radiation. So, an intense dose of radiation can cause a lot of ionization in a cell, which can kill the cell. So this is what happens when someone suffers radiation burns. The cells affected simply die as if they had been burned. If the sufferer is lucky and receives suitable treatment, the tissue may regrow. So an intense dose of radiation can damage living cells. It can burn them. Okay, so this is 1. Then we have 2, if the DNA in the cell nucleus is damaged. Okay, so when we receive a dose of radiation, if the DNA in the cell nucleus is damaged, the mechanisms that control the cell may break down. And so this would cause the cell to divide uncontrollably and a tumor will form. So this is how radiation can cause cancer. Okay, the third way radiation can damage living cells is this. If the affected cell is a gamete, a sperm or an egg cell, the damaged DNA of its genes may be passed on to future generations. And so this is how radiation can produce genetic mutations. Occasionally, a mutation can be beneficial to the offspring, but more usually, it is harmful. A fertilized egg cell may not develop at all, or the baby may have some form of genetic disorder. So this is how radiation can produce genetic mutations. So we are least likely to be harmed by alpha radiation coming from a source outside our bodies. This is because the radiation is entirely absorbed by the layer of dead skin cells on the outside of our bodies and by our clothes as well. So the radiation coming from a source outside our bodies is not that harmful to us. However, if an alpha source gets inside us, it can be very damaging because this radiation is highly ionizing. That is why radon and thoron gases are so dangerous. We breathe them into our lungs where they irradiate us from the inside. And the result may be lung cancer. So today we know more about radiation and the safe handling of radioactive materials than ever before. So knowing how to reduce the hazards of radiation means that we can learn to live safely with it and put it to many worthwhile purposes. So now we're going to see some of the many uses to which radioisotopes have been put. We will look at these uses in 4 separate groups. 1. Uses related to their different penetrating powers. 2. Uses related to the damage their radiation causes to living cells. 3. Uses related to the fact that we can detect tiny quantities of radioactive substances. And 4. Uses related to radioactive decay and half-life. So, let's start with uses related to penetrating power. Okay, so we have smoke detectors. These are often found in domestic kitchens and in public buildings such as offices and hotels. So if you open a smoke detector to replace the battery, you may see a yellow and black radiation hazard warning sign. So the radioactive material used in smoke detectors is americium-241, a source of alpha radiation. So how does this smoke detector work? What happens is that the radiation from the source falls on a detector, and since alpha radiation is charged, a small current flows in the detector. So the output from the processing circuit is off, so the alarm is silent. But when smoke enters the gap between the source and the detector, it absorbs the alpha radiation. Now no current flows in the detector and the processing circuit switches on, sounding the alarm. So this is the smoke detector. It detects smoke. It may be fire smoke, and the smoke absorbs the alpha radiation, so the current stops flowing in the detector. And the processing circuit switches on, sounding the alarm. This is also kind of related to fire alarms. Okay, so we have another use related to penetrating power, which is thickness measurements. So, in industry, beta radiation is often used in measuring thickness. So manufacturers of paper need to be sure that their product is of uniform thickness. So to do this, beta radiation is directed through the paper as it comes off the production line. A detector then measures the amount of radiation level getting through the paper. If the paper is too thick, the radiation will be low and an automatic control system adjusts the thickness. The same technique is used in the manufacture of plastic sheeting. So beta radiation is used in this application because alpha radiation would be entirely absorbed by the paper or plastic. So yeah, that's the reason. And gamma radiation would hardly be affected because it is the most penetrating. So that is why we use beta radiation. Then we have another use, which is medical diagnosis. So the diagnosis of some diseases may be carried out using a source of gamma radiation. The patient is injected with a radioactive chemical that targets the problem area. It may accumulate in a bone, for example. So then a camera detects the radiation coming from the chemical and gives an image of the tissue under investigation. So this is how we can, use radioisotopes in medical diagnosis. We inject a person with a source of gamma radiation. I know this may be harmful, but it happens only once in a while, so it isn't that harmful for the patient. So the patient is injected with a radiochemical that targets the problem area. Then we can see that from a camera that detects the radiation. So then we can see an image of the tissue under investigation. Okay, last use related to penetrating power is fault detection. So fault detection in manufactured goods sometimes makes use of gamma rays. So for example, engineers are looking for any faults in some pipe work. So what they do is they strap a photographic film to the outside of the pipe. So a photographic film is strapped to the outside of the pipe and the radioactive source is placed on the inside. So yeah, the radioactive source is placed on the inside and a photographic film strapped on the outside. So when the film is developed, it looks like an X-ray and shows any faults in the welding. That's a cool way of detecting any faults. That's one way to do it for the pipe work. We do it in other ways for other things. Okay, so this is how we detect faults using the penetrating power of radioisotopes. So this was it for the uses of penetrating power. We have smoke detectors, thickness measurements that we also use, medical diagnosis, and lastly fault detection. So now we're going to move ahead on to looking at the uses related to cell damage. Starting first with radiation therapy. So a patient is receiving radiation treatment as part of a cure for cancer. So a source of gamma rays is directed at the tumor that is to be destroyed. The source moves around the patient, always aiming at the tumor. So in this way, other tissues receive only a small dose of radiation. Radiation therapy is often combined with chemotherapy, that is using chemical drugs to target and kill the cancerous cells. So here we have one use of cell damage. We use radiation to damage living cells, but they are obviously the bad cells, the cells which are forming a tumor. So if we do not end this tumor, it will keep on forming and it will get bigger and bigger. So we use radiation therapy as part of a cure for cancer. Then we have food irradiation. So food irradiation is a way of preserving food. because food often decays because of the action of microbes. So these can be killed using intense gamma rays. Because these organisms are single-celled, any cell damage kills the entire organisms. Okay, so this is food irradiation. So food often decays because of the action of microbes. But for example, if we don't have any microbes, then food would not decay. So this is how we preserve food. We kill these microbes using gamma rays, intense gamma rays. And because these microbes are single-celled, any cell damage kills the entire organism. So this is what food irradiation is. It's a way of preserving food. Then we have sterilization. You might have heard sterilization before as well. It is kind of like the cleaning of medical instruments. So sterilization of medical products works in the same way as food irradiation. Syringes, scalpels, and other instruments are sealed in plastic bags and then exposed to gamma radiation. Again, any microbes present are killed so that when the packaging is opened, the item can be guaranteed to be sterile. Sterile means completely free of germs, microbes. We use alcohol swabs to sterilize our skin. For example, when we're getting an injection, the doctors use an alcohol swab to clean the skin first so that it is sterile. Okay, so alcohol sterilizes the skin. So this is what sterilization is. Hope you've understood food irradiation, sterilization, and radiation therapy. Now we are going to move ahead onto looking at the uses related to detectability. How we can detect something. Starting first with radioactivity tracing. This is a very fun process. Every time you hear a Geiger counter click, it has detected the radioactive decay of a single atom. So this means that we can use radiation to detect tiny quantities of substances far smaller than can be detected by chemical means. And so such techniques are often known as radioactivity tracing. So what engineers do is that they inject water-containing radioactive chemical into a hole in the ground at high pressure. Then they monitor how it moves through underground cracks using gamma detectors at ground level. This is the water pipeline. So the engineer doesn't know there is a water pipeline. So when we inject water containing a radioactive chemical into a hole in the ground at a high pressure, it has to be at high pressure, then this Geiger counter can monitor the presence of this radioactive chemical and move along with it as it moves forwards. So then the engineers find out that there are some water cracks or water pipelines over here. So engineers may want to trace underground water. For example, they may be constructing a new waste dump, and they need to be sure that poisonous water from the dump will not flow into the local water supply. So this is what radioactivity tracing is. The second example is radioactivity labeling and genetic fingerprinting. So biochemists use radioactively labeled chemicals to monitor chemical reactions. The chemicals bond to particular parts of the molecules of interest so that they can be tracked throughout a complicated sequence of reactions. So the same technique is used to show up the pattern of a genetic fingerprint. Okay, so the radioactively labeled chemicals monitor chemical reactions, and the chemicals bond to particular parts of the molecules of interest. These are usually the unique molecules that are not found in any other organism, so that they can be tracked throughout a complicated sequence of reactions. Then we have half-life and dating. So, because radioactive substances decay at a rate we can determine, we can use them to discover how old objects and materials are. Isn't that amazing? The best known example of this is radiocarbon dating. So yeah, we can discover how old objects and materials are using radioactive decay. This is called radiocarbon dating. Okay, so all living things contain carbon. Plants get this from atmospheric carbon dioxide, which they use in photosynthesis. Plant-eating animals get it from the plants they eat to build their bodies. Meat-eating animals get it from their prey, which are plant eaters. So again, it's like a whole cycle of carbon. So most carbon is carbon-12, which is not radioactive. Only a tiny fraction is radioactive carbon-14 with a half-life of 5,370 years. That is a long half-life. And it emits beta radiation. So the idea of radiocarbon dating is when a living organism dies, the carbon-14 in its body decays. And as time passes, the amount remaining decreases. So if we can measure the amount remaining, we can work out when the organism was alive. Because carbon-14 has a very long half-life, it may be coming from a very long time ago. So now let's see how we can measure the amount of carbon-14 in an object. There are two ways to measure carbon-14 in an object. Number one, by measuring the activity of the sample using a detector such as a Geiger counter. Number two, by counting the number of carbon-14 atoms using a mass spectrometer. Okay, so we can use any of the two ways to measure the amount of carbon-14 present in an object. So this is how we use radioactivity. The carbon-14 is a radioactive substance, so we use that carbon-14 to measure how old an object or material was. So problems can arise with radiocarbon dating. It may be that the amount of carbon-14 present in the atmosphere was different in the past. Certainly, nuclear weapons testing added extra carbon-14 to the atmosphere during the 1950s and the 1960s. So that was because they used to test these weapons on the ground or in the air, which was very harmful as it used to bring a lot of carbon-14 to the atmosphere. Nowadays, these nuclear weapons testing is done underground, so this carbon-14 has decreased. But this means that living objects that died then have an excess of carbon-14, making them appear younger than they really are. So, geologists use a radioactive dating technique to find the age of some rocks. Many rocks contain a radioactive isotope, potassium-40. This decays by beta emission to a stable isotope of argon. So argon is a gas and it is trapped in the rocks as the potassium decays. The rocks of interest form from molten material. So there is no argon in the molten rock because it can bubble out. After the rock solidifies, the amount of trapped argon gradually increases as the potassium decays. So geologists take a sample and measure the relative amounts of argon and potassium. The greater the proportion of argon, the older the rock must be. So this is another technique geologists use to find the age of some rocks, the proportion of argon and potassium. So this was it for uses related to detectability. This was the last use of radioisotopes, in which we read about radioactivity tracing, radioactive labeling, and genetic fingerprinting, and lastly the half-life in dating, which is really a very good discovery of scientists. So finally we completed the 4 uses of radioisotopes, uses related to the different penetrating powers, in which we read about smoke detectors, how we can measure the thickness of some papers, and the medical diagnosis and fault detection. Then the uses related to the damage their radiation causes to living cells, in which we read about the radiation therapy, food irradiation, sterilization, and then we looked at the uses related to the fact that we can detect tiny quantities of radioactive substances, in which we read about radioactivity tracing, radioactivity labeling, and genetic fingerprinting. And then we saw uses related to the radioactive decay and half-life, which was half-life and dating. So this was it for radioisotopes. I hope you've understood it. What radioisotopes are, you remember that as well. So now we are going to move ahead on to understanding what nuclear fission is. So, nuclear fission. In one of the previous topics, we saw why radioactive decay occurs. What happens is that an unstable nucleus becomes more stable by emitting a small particle, either alpha or beta, and usually some electromagnetic radiation, gamma rays. So, nuclear fission is another way in which an unstable nucleus can become stable. So, in nuclear fission, a large nucleus splits to form two smaller nuclei. Some neutrons are also released, so this is what nuclear fission is. A large nucleus splits to form two smaller nuclei and some neutrons are released. Okay, so the word fission means splitting. So think of a fissure, which is a large crack in a rock. So this is what nuclear fission is. So there are two ways in which a fission can occur. Sometimes a large unstable nuclei will split spontaneously. So this is spontaneous fission. In the other kind of fission, a neutron collides with a large nucleus, making it even more unstable and causing it to split. So this is neutron-induced fission. We're going to concentrate on this second mechanism because it is the one which is made use of in nuclear power stations and in nuclear bombs. So we ourselves induce fission using the neutrons. Okay, so here is what happens in nuclear fission. This is neutron-induced fission. Here we have a uranium nucleus undergoing fission. A neutron hits the uranium nucleus and is absorbed, okay? The nucleus is now very unstable and starts to deform, okay? So we remembered how isotopes are. Some isotopes are stable and some are not. That is because the neutron number is more than the proton number, it's not equal, so they are not very balanced. So when a neutron gets absorbed by this nucleus, it becomes unstable and starts to deform, something like this. Soon it splits completely in two to form two daughter nuclei. At the same time, 2 or 3 neutrons are released, okay? And also a lot of energy is released. So let's see how this process releases energy and how it is helpful for us. So this process releases energy which was previously stored in the uranium nucleus. Okay, this energy takes these following forms. So the daughter nuclei move apart. They have kinetic energy, okay? So how do they move apart? They have kinetic energy, some sort of energy that makes them move apart. Secondly, the neutrons also fly off at high speed. So they too have kinetic energy. And lastly, gamma rays are released. This is energy in the form of photons of electromagnetic radiation. We've read this previously as well in beta decay, that energy is released in the form of kinetic energy and the gamma rays. In nuclear fission, 2 daughter nuclei move apart, okay? So that's a different kind of thing, but it still has kinetic energy. So when a single uranium nucleus splits like this, the energy released is about 10 in the power of minus 11 joules. So this is a very tiny amount, but it is much more than the energy released in a chemical reaction. Hence, we can think of uranium as a highly concentrated source of energy, roughly 1 million times as concentrated as an equal mass of coal and oxygen. So, compared to coal and oxygen, nuclear fission produces a lot of energy, more energy, okay? So that is the reason why nuclear power stations are more liked than coal power stations. First of all, coal power stations produce a lot of pollution, okay? Because coal turns into ash. Nuclear power stations do not produce that much of waste, but they also do have their hazards. Unlike coal, they do not transform into ash, so they cannot be dumped anywhere. The radioactive materials are highly dangerous, so they have to be dealt with afterwards. We're going to see more about the nuclear power stations later on. Let's focus on nuclear fission for now. So now we're going to see chain reactions. So like one reaction causes another reaction, that reaction causes another reaction. This is the sort of thing what I'm talking about here. So fission releases neutrons which fly off at high speed, perhaps 10 in the power of 7 meters per second. So each of these neutrons may collide with another uranium nucleus and cause it to split. Then, through this reaction, more neutrons are released, and these may cause more uranium nuclei to split. So the result can be a chain reaction. So in a nuclear power station, the chain reaction is kept under control. The reactor is designed so that just one of the neutrons goes on to cause another to split. The other neutrons escape from the uranium and are absorbed by the surrounding concrete. So this chain reaction is hindered. The process of this chain reaction is hindered this way because the neutrons released, they get absorbed by the surrounding concrete. In a nuclear bomb, this is something different than a nuclear power station. In a nuclear bomb, the idea is to get as many uranium nuclei as possible to undergo fission in a very short time. So from the first fission, perhaps 2 neutrons go on to cause uranium nuclei to split, releasing 4 neutrons which cause fission, then 8, 16, and so on. So the nuclear reaction escalates out of control and vast amounts of energy are released in a fraction of a second. So this is nuclear fission. This is also nuclear bombs, which are highly dangerous, Okay, so this is nuclear. This is what a nuclear bomb is and what a nuclear power station is. In a nuclear power station, the chain reaction is kept under control, whereas in a nuclear bomb, the idea is to get as many uranium nuclei as possible to undergo fission in a very short time. Okay, so the reactor in a nuclear power station is designed so that this cannot happen. The biggest danger is that the reaction may go so fast that the uranium overheats. It may melt and the reactor may burst into flames. So that is also dangerous. So that is why we keep these chain reactions under control, because we don't want this to happen, okay? The uranium getting overheated and melting in the reactor, bursting into flames, nobody wants this. So that is why the nuclear reactor is surrounded by concrete, so that the neutrons escaped from the uranium are absorbed by the surrounding concrete. Okay, so hopefully you've understood the chain reaction and how nuclear fission releases energy. We're going to move ahead onto the radioactive products. The radioactive products this nuclear fission produces. So a uranium nucleus splits to produce 2 daughter nuclei. These daughter nuclei are almost always unstable. That is, they are radioisotopes which undergo radioactive decay. So this is the big problem with using uranium as a fuel. It doesn't result in ash. Like in coal power stations, the coal burns to release energy and in the end it forms ash, which can be, it can be dumped anywhere, okay? So that's a different thing. But with nuclear fission, the uranium produces radioactive products. The products it produces are radioactive as well. And so, of course, we cannot dump radioactive products anywhere we like because it's dangerous. So we have to deal with them. So this is the big problem with using uranium as a fuel. It doesn't really result in ash. Instead, radioactive waste is produced and has to be dealt with. Some of the radioisotopes are highly radioactive, but that can be a good thing. After a few years, their activity will have decreased to a safe level. Others are less radioactive, and this means they must be stored safely for a long time, perhaps centuries, until they are safe to release to the environment. So it is difficult to decide the best way to deal with these dangerous materials. Is it best to concentrate them so that only a small volume of highly dangerous material must be stored, or is it best to keep them in a more dilute form? This is a problem which still remains to be solved. But still, nuclear fission itself is a very useful process. It may produce dangerous materials, but we can deal with them. Overall, it helps in producing a lot of energy. So we're going to see how we can make use of nuclear fission by looking at a nuclear power station. So now we're going to see inside a nuclear power station. So the electricity generated by a nuclear power station is exactly the same as the electricity from any other power station. Any other power station, by this we mean like a coal power station, even though it produces a lot of pollution, but still, nuclear power stations produce the same electricity as any nuclear power station. So let's see the difference between a nuclear power station and a coal-fired station. In a nuclear power station, heat is generated in a nuclear reactor by the fission of uranium. This energy is transferred by a coolant to a boiler which generates steam. So, this is nuclear power station. In a coal-fired station, burning coal produces heat which heats the water in a boiler to make steam. So as you can see that in both cases, steam from the boiler is used to turn turbines which turn generators. But the process to heat the water and produce the steam is different because we need energy to boil water to generate steam. This energy is produced by the nuclear reactor in nuclear power station, and in coal-fired station, burning coal produces this heat. Okay, so there are several different designs of nuclear reactor in use around the world. Let's see a typical reactor. So in this typical reactor, we have some features to notice. We're going to look through them one by one. One feature to notice in a nuclear reactor, in a typical nuclear reactor, let's say, is the fuel. The fuel in this reactor is in the form of rods, and inside each fuel rod, the fuel is in the form of pellets. So a spent rod can be removed and replaced while the reactor is running. So this is the first thing to notice about a nuclear reactor. The fuel in the nuclear reactor is in the form of rods. Okay, so between these fuel rods are blocks of graphite which form the moderator. So without the moderator, the neutrons are slowed as they pass through the graphite, making them more likely to interact with uranium nuclei, and you know what happens next. It may cause explosion or something, because we don't want them to interact with uranium nuclei more, because we don't want to produce excessive heat. So this is where a moderator comes in. The moderator keeps the neutrons moving fast. So these blocks of graphite form the moderator. Also passing through the graphite are control rods. These are made of a material which is good at absorbing neutrons. We use boron as this material. These control rods can be lowered into the reactor to slow or stop the reaction. They can be removed to speed it up. So they basically are called control rods because we control the rate of the reaction through these. So this material boron is good at absorbing neutrons. So whenever the reaction is getting too fast and is producing a lot of heat, we can lower these control rods and they would absorb the neutrons. And so they can slow or stop the reaction. And if the reaction is getting too slow, they can be removed to speed it up. Lastly, we have the coolant. The coolant is the carbon dioxide gas. This is pumped along pipes in the hot core of the reactor, where it heats up. So, the hot gas then passes down through pipes in the boiler, resulting in high pressure steam. So, this is the part we were talking about in the beginning of this chapter, that energy is transferred by a coolant, such as carbon dioxide gas, to a boiler which generates steam. So the coolant is a carbon dioxide gas, and this is pumped along pipes in the hot core of the reactor where it heats up. The hot gas then passes down through pipes in the boiler, resulting in high pressure steam. Okay, so this coolant transfers heat, transfers energy from the nuclear reactor to the boiler. Okay, that results in high pressure steam. Okay, so the coolant passes through pipes in the core so that it isn't contaminated by the core's radioactivity. The core is surrounded by thick layers of concrete which absorb neutrons which escape from it. So, to prevent contamination, the coolant passes through pipes in the core so that it isn't contaminated by the core's radioactivity. So this is what a nuclear reactor is like. A typical nuclear reactor is like. So there are several different designs of nuclear reactors in use around the world, but this is a typical one. Here you can see a diagram. This is the core of the nuclear reactor. This is the reactor core. Here we have the control rods, the concrete shield shielding this entire thing to absorb neutrons. The moderator is this one here, these black kind of lines. These green lines are the control rods. These yellow lines are the fuel rods. Steel pressure, this is the steel pressure vessel in which all of these are kept. And here we have the boiler, or in other words, steam generator. The hot coolant comes here and heats up this water, and the steam is generated, which produces the electricity, which generates electricity. Here we have the electricity generating plant. So this steam goes over here and electricity is generated here. Then the cool water comes from this generating plant. After all the energy is used up, the cool water then comes back here, gets heat up over here again, and then the steam is again. So this is a kind of like a cycle. The cool water comes from the electricity generating plant. The hot coolant warms it up again, boils it up again, and then the steam goes and flows into the electricity generating plant, and then again it is pumped from it. So this is this kind of thing. The cool coolant goes into this nuclear reactor, it warms it up again, it makes it warm, and then the hot coolant comes here again. This is also kind of a cycle. It keeps on happening, and this whole nuclear reactor is kept at a steady rate. The energy being produced is kept at a steady rate so that it doesn't overheat or underheat or something. Using these control rods, they are lowered down if it is producing too much energy and removed if it is making too less energy. So this is a nuclear power station. I hope you've understood this. Nuclear power stations play a very important role in the world creating energy. And this is better than the coal power station because, first of all, nuclear energy never gets used up. It can be produced more and more. Because in nuclear power station, we do not use the spontaneous fission, we use the neutron-induced fission, which man can do by itself. So radioactive materials never get used up. Whereas coal is a fossil fuel, and this can be used up. One day there will be no coal and we won't be able to produce energy. Some countries are here which still use coal power stations, but it is suggested to use nuclear power stations because in nuclear power station the energy is unlimited. It can be produced on for ages and it never gets used up. That is why modern industry is switching to nuclear power stations from coal power stations, because coal is a fossil fuel and we know that one day it will end and we won't be able to make more energy. One thing is that nuclear power stations are a little expensive to build because of the entire thing. So that is why some countries which are not that modern still use coal power stations. Okay, so this was a nuclear reactor, a nuclear power station. The reactor, what happens in the reactor, the different features we learned about a nuclear power station, a nuclear reactor. I hope you've understood it and this is clear to you, and I hope it was also very fun to understand this. So now that we've understood nuclear fission and the nuclear power station, we are going to move ahead onto the last topic of this chapter, nuclear fusion. Okay, so this may sound very similar to nuclear fission, but it is different. In nuclear fission, a nucleus splits to form two nuclei. But in nuclear fusion, two small nuclei come together and join to form a larger nucleus, releasing energy. So these are very different and opposite things to each other. In nuclear fission, one nucleus splits to form two nuclei, releasing energy. And in nuclear fusion, two small nuclei come together and join to form a larger nucleus, releasing energy. You know the word fusion, it means melting together. The fusion of two small nuclei. So here we have an example of nuclear fusion. Two hydrogen nuclei fuse together to form a helium nucleus. So here you can see these are two different isotopes of hydrogen. There's the deuterium and the tritium isotope of hydrogen. So the equation for this reaction would be the deuterium plus the tritium arrow, which represents the change in when they both get together, they fuse together, they form a helium and a neutron. Don't forget, a neutron again is released, just like in nuclear fission. So a neutron is released in this way. If, for example, we don't have deuterium in here, but the common form of hydrogen, then we know that in the common form of hydrogen, the hydrogen has one proton only. There is no neutron in the hydrogen. So if we have the common form of hydrogen instead of the deuterium, there would be no neutron getting produced in the end. There would only be the helium being produced, because this neutron is the extra neutron. If there was only the common form of hydrogen, there would be no neutron here, and one proton from the hydrogen and two neutrons and one proton from the tritium would produce the helium. So this is a different thing I was just talking about. I was just telling that this neutron ends up being alone in the end. Okay, so this is what nuclear fusion is basically. Two different nuclei fuse together to form a larger nucleus, and it releases energy. Don't forget that. So fortunately for us, nuclear fission is a rare event on Earth. Otherwise, whenever two hydrogen atoms met, they might fuse to make helium, and the result would be no water and no life. So it's good that nuclear fusion is a rare event on Earth. In practice, nuclear fusion requires very high temperature to work. The reason is that nuclei are all positively charged and repel one another. So if they can get close enough together, the strong nuclear force will overcome the repulsion and they will fuse together. So it is only at high temperatures that nuclei are moving so fast that they can approach one another close enough to fuse. That is why the nuclear reactors, which have the nuclear fusion happening in them, are more expensive to build, because they need even more energies, even more high temperatures for the fusion to take place. So that is because the nuclei are positively charged and they will not get close together because they will repel each other. Only at high temperatures will they be able to get close enough to fuse. So physicists and engineers hope to produce a new generation of power stations which use nuclear fusion instead of nuclear fission. These should be cleaner than uranium-fueled reactors because they would produce much less radioactive waste. This is one of the good things about nuclear fusion. The problem with nuclear fusion is to control a fusion reaction, which will only happen at temperatures of about 100 million degrees, as I was talking about before. So it may be several decades before a commercially viable fusion reactor is operational. But still, one day this will also happen. Has there anything that we've thought about never happened in life? No, right? Artificial intelligence is also now in the world. Something we used to think about but never really believed that it will happen. But now it is happening. So one day nuclear fusion reactors would be also happening. A hydrogen bomb is a type of nuclear weapon that uses fusion. Hydrogen atoms fuse together to release large amounts of energy. A small fission bomb is used as the trigger which generates the higher temperatures and pressures necessary to set off the fusion reaction. So, this was nuclear fusion. Nuclear fusion is the total opposite of nuclear fission, yet both the processes release vast amounts of energy. Nuclear fusion is better than nuclear fission because it produces less radioactive waste. So that is why we are thinking to move from nuclear fission to nuclear fusion in the future. Okay, so now that we've understood nuclear fusion, what it is, it's pretty simple to understand. I know it's just like two nuclei fusing and forming a larger nucleus, whereas nuclear fission is one nucleus splitting to form two nuclei, both releasing energy, vast amounts of energy. So now we're going to see the nuclear fusion in the stars. What is that? So yeah, nuclear fusion does happen in stars. Let's see what that is. So stars such as the sun are very hot. They formed from clouds of gas and dust which collapsed under their own gravitational pull. So as their particles collided together, they got hotter and hotter. Consequently, the temperature inside a star is hot enough for nuclear fusion to take place. So, engineers say and physicists say that we will not be able to do nuclear fusion as it is happening inside the star. Because in a star, the temperature is really, really hot. It is so hot that nuclear fusion takes place. And do you know how much nuclear fusion is taking place every second? In the sun, hydrogen nuclei are constantly fusing together, releasing 4 into 10 in the power of 26 joules of energy every second. So this is really, really a lot of energy. And physicists and engineers say that we will not be able to produce this much energy using nuclear fusion ever in our lives. Ever, because we would not be able to reach such high temperatures to produce this much energy. And of course, we do not want to produce this much energy as well, because we don't want our planet to become a star, do we? So here are some examples of what can happen when 2 carbon nuclei fuse together in a very hot star. So here we have 2 carbon nuclei. These are the normal, these are not isotopes, these are not radioactive, they are just simple carbon nuclei fusing together to form magnesium atom and energy. Here they are forming to produce the neon atom and helium atom and energy. Here they are forming to produce an oxygen atom and 2 helium atoms and energy. So these are some predictions of what can happen when 2 carbon nuclei fuse together in a very hot star. So this fusion reaction can produce 3 elements: magnesium, neon, and oxygen. Astronomers sometimes talk of stars cooking elements, and this is even more misleading than talking about burning uranium in a reactor. Eventually, the star finally explodes and all of these elements are spread through space. Later, a new star forms together with its planets. The planets contain carbon, oxygen, etc. Just the elements needed for life, And that is where these elements in our bodies came from. The ash from the explosion of a long dead star. That is how the Earth formed one day. That is how our sun formed and the planets formed around this sun. The Earth formed. That physicists and scientists found some rocks on Earth, which when they found how old they were using radiocarbon dating, they found that these rocks were even older than the Earth formed. So this suggests that the Earth also came to life from the ash from the explosion of a long dead star. So that is where these elements in our bodies came from, and the elements on the Earth came from. The elements needed for life. So anyways, that we just get into a lot of different stuff from there and we just lose our direction. But this was it for today's chapter, Radioactivity. Congratulations for completing the last chapter of our Physics O-Level series. I hope you enjoyed this course as much as I did, and this last chapter was very fun too. I hope you've understood everything in detail and would remember it. All the things, all the different topics we read in this chapter, starting with radioactivity, what background radiation was, the sources of some artificial radiation, how we can detect radiation, the 3 different types of radiation, alpha, beta, and gamma, radioactive decay equations, deflecting radiation and the penetrating power of the 3 radiations, also the ionization of the 3 radiation, the radioactive decay, what that was, how we can measure the half-life, and also radioisotopes, what the uses of radioisotopes were, including we read about half-life and dating, radiocarbon dating. Then we understood nuclear fission, nuclear fusion, and nuclear power stations. So as you can see, this radioactivity chapter was a very detailed and big chapter, but also a very fun chapter. I hope you will memorize everything in this chapter, the different equations we learned, and also the nuclear fission and fusion. So, thanks for watching this video. And after this physics O-level course, I am going to start my new O-level series, which is going to be of chemistry. So I will hope to see you in that chapter soon.